Thank you. Good morning, and good morning to everyone who's joining us online too. I've just had a WhatsApp. Apparently my team are all dialed in on the Zoom, so hello to you as well. So I'm going to talk to you today about something which started out as an optimization exercise, so a series of very small changes, but has now turned into something much bigger. But first of all, let me tell you about something that was never intended to be small. This is the SS Great Britain. So the SS Great Britain was launched in 1843, and she was the world's first iron ship. And she was also the first to be driven by a screw propeller. Now, this combination means that she was a huge technological milestone. Essentially, she was the first modern ocean liner. Her iron structure was designed by the well-known engineer Isambard Kingdom Brunel, and it allowed her to be bigger than had ever been possible before. It also allowed her to survive being run aground right at the very beginning of her career. Now, this ordeal actually bankrupted the company that built the ship, but the ship survived. And the ship went on to become the fastest and most comfortable way to emigrate from Britain to Australia. So that same iron hull allowed the ship to be refitted, reconfigured, repurposed, recycled. You can see where I'm going with this. She sailed more than 1 million miles. She transported thousands of passengers before eventually she was abandoned in Sparrow Cove in the Falkland Islands. And this was almost a century after her launch. In 1970, the ship was salvaged and she was towed 8,000 miles back to Bristol. In fact, back to the same Bristol dry dock which had been constructed in order to build the ship. So this combination, this historic combination of ship and dry dock has been almost, excluding a bit of time in 20 and 2021, almost continuously accessible to the public in some way. Unfortunately, we did have to break that record during the pandemic. So at first, when she was back in Bristol, the ship was cared for by traditional engineers, but the combination of Bristol's climate and the amount of salt embedded in the iron meant that once the lower hull got out of the water, it was subject to really aggressive corrosion. And that was putting the material at risk of being permanently lost, basically. So in the 90s, the ship got her first curator, who led the design of a world-first conservation system, which was focused on preserving that original material, which hopefully I've put enough information in to make you understand why we're wanting to preserve that original material. Now, the top sides, they can be protected with paint, but because of the higher salt concentration below the waterline, the only way to stop the ship from disintegrating completely is to stop that chemical reaction. And to do that, we have to remove one of the kind of elements that's taking part in the reaction. So we've got two options. We've got oxygen and water. So to create a great visitor experience, we should probably keep the oxygen. So we conserve the hull by keeping it very dry. And the research tells us that 20% relative humidity should be our target. That's about equivalent to the Arizona desert. A glass roof on the dry dock at the waterline creates a seal around the bottom part of the hull. And the glass is flooded with about 2 inches of water. So from above, the ship looks like she's ready to set sail. But underneath, we have 2 custom-built desiccant dehumidifiers, and they deliver dried air to the most vulnerable parts of the material. We've got one on the inside and one on the outside of the lower hull. Now, we're an independent museum, so we rely on ticket sales to cover the costs of running this system. So we put the system on display. Part of the visitor experience, in fact, is to go underneath the ship and to see exactly what your ticket money is being spent on. And this has been pretty successful. The environment around the ship has now been held more or less stable for well over a decade. So coming on to the climate change issue, we were told by the original designers of this system that unfortunately it would always have to run on fossil fuels. We needed gas, we needed to burn gas in order to, for the drying action of the dehumidifiers. And that was just because of the speed that they would need to respond and also the temperature that they would need to get to. So energy efficiency was considered really carefully in the design of this system. So to start with, we've got only the parts of the hull that really needed it inside the climate-controlled envelope. The air itself, even once you're inside, is delivered in really carefully chosen locations to create a layer of air, a curtain of air over the iron. We use water from the harbour for the cooling system in the dehumidifiers, and even the layer of water on top of the glacis, as well as looking pretty, it actually provides an insulation benefit. But now that we've got some experience operating this system, and with energy efficiency more important than it has ever been, the time was right to ask, can we do even better? And so in 2018, a new role was created to try and answer that question, the ship's conservation engineer. I've been introduced about 3 times now. So what I want to say, though, is that I came into this job knowing almost nothing at all about ships. So no hard questions about that, please. And also having never worked in a museum before. But that also meant that I came in with no preconceptions about how things should be done on this project. And what I found was that the individual components on the dehumidifiers were being really well maintained by our fantastic team of site technicians and with the help of contractors. But what this new role has allowed us to do is to develop our own in-house understanding of how the system as a whole, the whole system, not the individual bits and pieces, how it really operates together. And it's also allowed us to identify what we call the unknown unknowns. So those are the problems that we didn't know we had. So kind of making more work for ourselves here, but you know, it's all worthwhile. So we had a computer system which showed me that the average humidity in the space was mostly pretty close to the target, so that's good. But when I dug a bit deeper into the software, I discovered 2 things. Firstly, some of the individual sensors that were making up that average were not sending us data very often. So there was quite a long delay before any change in the conditions, so if it started raining, for example, was getting communicated back to the control system. And secondly, that almost every internal component on the dehumidifiers had its own set of sensors, so potentially we had a lot of data. But that the software system for accessing this data, for using this data, was obsolete, and in fact I couldn't find any evidence that it had ever been used. So we did some fundraising, thinking that if we could see a bit better what was going on, then we would be able to fine-tune the controls, and hopefully we would be able to save some energy. That was the plan. So now I have some new toys. And I can see the humidity live from anywhere on board the ship, and also I can click on any component of the dehumidifier and I can pull up a graph and I can show what's happening with that specific component, and I can drag and drop other components on too, so I can compare them, and I can look at it today, last week, last month. And so by doing this, we can start to understand exactly what the system is doing, and if we're getting any deviations from our target humidity, we can start to understand why. And I can also now see the computer program which controls this system. And with some careful experimentation and a bit of help from Wikipedia, we've been able to understand the controls. So we now have a really good feel for how the system works, exactly what it does. And all of this new insight has allowed us to start asking our maintenance contractors some more detailed questions. Not only about making sure it all works, but about how we should be running it to get the best performance out of it. And once we were having these more in-depth conversations, something really remarkable started to happen, and opportunities to do much bigger things suddenly started to come out of the woodwork. Now, I'm going to tell you about just one of those today. So our local authority runs a scheme. It's called the Green Business Grant Scheme, and it's a series of small grants, a bit of funding, and the idea is that it helps small businesses such as ourselves to reduce their carbon footprint. So we applied for a Green Business Grant, and they sent their technical advisor around to survey our site, and they had a look at all of the stuff that we were doing, and they came back to us with a proposal. They said, we think you should get some more energy efficient lighting, and we think you should put some better insulation on the valves in your plant room. And that was going to save us around, that was going to reduce our emissions by around 7.5 tonnes of CO2 per year. Remember that number. But with our new expertise, we went back to them with a counter proposal. And we asked whether they would instead consider funding something that wasn't on their list, and it was an energy recovery system. I don't have time to explain how that works today, unfortunately. An energy recovery system that we had been thinking about whether we should install. And so we had another conversation with the technical advisor. We were able to explain how it worked, and we were able to tell them that we thought it would save us emissions of 100 tonnes of CO2 per year. And obviously he wanted to check those calculations, so we then facilitated a conversation with the supplier of the equipment, and eventually they decided that yes, we could have the grant. It was a much bigger grant than they'd originally offered us to install this system. So unfortunately it's not a very glamorous looking system, although the contractor who installed it did install a sexy green light just to show everybody how green it is. And I can explain how it works, but you'll have to find me at lunchtime if you want the full story. But essentially, it recycles heat from inside the system. So while we were in the process of installing that, I started reading up a bit more on how it worked. And I realised that one of the things that we would need to do once it was installed was that we would need to do some more damping down, so some more readjustment of the control algorithms. But by this point, we're pretty confident with those, so that was good. And about a week after we installed this kit, I hit save on a new code and it didn't crash. And so now we've got this new system running, and we've also got the control algorithms kind of tuned. And the combination of these things, when you put it all together, as well as some of the other smaller things that I haven't had time to talk to you today, the results that we've had from this have been better than I could possibly have imagined that they would be. So for example, the bigger of our two dehumidifiers, which is the one that does the inside of the ship, in the first half of this year, that dehumidifier burned 40% less gas than it did during the equivalent period last year. So going back to the software and the graphs and all that stuff, I went into my new software and I generated a graph. So it's not the prettiest, but it's real life data. And that shows the temperature that the drying system is operating at. So if you can remember back a few minutes, those temperatures, high temperatures, were the reason why we'd been told in the past that this system would always have to run on fossil fuels. So I did a bit of reading. So here's the yeah, there we go, there's the data. So it's not very pretty, but it's real life data. And you can see just over halfway along from left to right is the time when we kind of finished installing all of our new kit. And you can see that that temperature has reduced. So I did a bit of reading to try and figure out how much that temperature would need to reduce by for us to be able to ditch the gas and get our heat potentially from a greener source. And now I think we might be getting close. So I didn't know that this was even possible when I started this work, and much as I would like to pretend it was all planned, I'm not going to. And I certainly did not set out with the intention of proving anybody wrong about anything. I just wanted to make whatever savings that I could. But what I think we've learned from this is that you can hire the best consultant in the world, but the advice that you get from them is only ever going to be as good as the information that you can give them to work from. There was nothing wrong with any of their reports, apart from the fact that they were all written based on the information that we had given them, which was incomplete. It didn't take into account the whole situation. So it is worthwhile, I think, trying to develop, especially in this sector, we're very specialised, trying to develop your own understanding of your own unique problem, even if you're then going to hand it over to somebody else to try and solve it. Because they will come up with a better solution if you can give them a better idea of what's going on. So our next challenge then is to try and figure out exactly how we're going to get a lower carbon heat supply into our system. And you won't be surprised to learn from the theme of the talk so far that currently I do not know how we're going to do that. We have some potential ideas that we're working on. And I'm not entirely sure how it is going to look, but I do believe that it can be done. Now, we've heard some really amazing stuff earlier in this week about carbon capture in the ocean and about renewables, but with carbon capture in the ocean, we've also heard just how complicated that is. And actually, the same is true for renewable energy. While there are some really amazing innovations out there, they still have all of them have an environmental opportunity cost. So it might be a bit less glamorous, but reducing our consumption, or at least stopping it from increasing as we are all trying to expand what we do, is just as important as all of those technologies. In fact, I think it's more important. And actually, that's without even mentioning the bottom line, and this is an afterthought, and actually maybe it should be a headline. Of course, this work is well on the way to paying for itself. Now, a few people have included a call to action in their talks this week, so here's mine. The mayor of Bristol recently got into trouble with the local press. And the reason he got in trouble with the local press was because he flew to Canada, he flew to Vancouver to give a 15-minute TED Talk. Now, I realise that this event is about so much more than the speakers on the stage, and it's been an absolute privilege to meet with so many of you this week. But I'm going to finish with one quick sum, and that's that the work that I've described that we've been doing on the SS Great Britain has reduced our annual CO2 emissions by an amount which is roughly equivalent to flying 100 people from London to Halifax and back. So, here's the deal. If by being here in person, I can persuade you to look a bit closer at your organisation's energy, and if everyone in this room combined can make even 1% of the saving that we have, then my flight here to speak to you today will have had a net positive impact. I would really like you to help me make that a reality. And what I would like even more is if you could get in touch and tell us what you're doing, however small that may be. I don't care how small it is, I want to know about it. And who knows, maybe you'll start with something really small and you'll discover something much bigger. Thank you.
I think that was a really good example that, you know, no matter what the context of the presentation is, it's how you present it and how you deliver it that makes it interesting. I would have read that and thought, I'm not really going to listen to that.